o empiezo en inglés y ya está. Okay, so welcome to this presentation named Integrated Sensing and Communication, Fundamental Limits, Metrics, and Open Issues. I'm Máximo Morales Céspedes from the Group of Communications of the Department of Signal Theory and Communications, and basically this presentation is going to, or pretend to be an introduction to ISAC, to this concept of integrated sensing and communication. So what we know nowadays about integrated sensing and communication. So we know that there are two different worlds in general. So we have this sensing-centric design. Probably here in the group of communication, this is far from our knowledge, or a bit far from our knowledge, because we are used to the communication world. So basically, when we want to sense something, when we want to determine their position or some parameter related with a target, we transmit a deterministic signal, and we want to determine the impact of the environment with the signal that we receive according to that deterministic signal that we transmitted before. Traditionally, there is the concept of radar, of monostatic radar, when we use the reflection of the signal, but this is maybe not the case. We can use also bi-static radar. For instance, if we want to transmit a signal, deterministic signal, we receive that signal far away, and we want to know what happened in the environment. And we have also the communication-centric design, in which we basically want to increase the entropy of the transmitted signal according to the capacity. So here is the fundamental limits of communication, very well known for everybody here. Basically, when we want to obtain the Shannon capacity, basically we want to maximize the mutual information according to variable x and y. So this is the classical equation of the capacities. Then if we have a multi-user system, basically we have the sum of the capacities, and also we traditionally focus on other metrics such as spectral efficiency, bit error rate, etc. So I mean, this is very well known for everybody here. At least in my humble opinion, the fundamental limits of sensing are more unknown for us, at least for me. So here, when we say sensing, when we say integrated sensing and communication, what is sensing? It's something that I ask many times. So we have three ingredients here for sensing. We have detection. So basically, we are transmitting to some direction, and we want to know if somebody is located in that direction. So this is the detection of if somebody is there, basically. So this is the two hypothesis case, and this is at least I think that this is a classical problem of communication theory, or this is we studied it during the degree, but we usually don't use it in communications. So basically, the hypothesis 0 is the measurement of noise, that nobody is there, and the hypothesis 1, it means that we receive the reflection, or we receive something. It's not necessary to be the reflection. Be careful here. We receive something plus the noise. So if we assume that we know the probability density functions of this of the observation given the hypothesis, we can obtain the probability of detection and the probability of false alarm. This is well known. I mean, we studied this in the second or the third year of our degree. Maybe we don't remember it, but it's easy to obtain. So probably you remember this, and basically this is the solution to this problem is the Niemann Pearson rule, in which basically we define a threshold, and we can say, okay, we want to be subject to this level of probability of false alarm or probability of detection, and we optimize the other probability. That means I want a probability of false alarm lower than 10 minus 4. Then I can maximize or optimize the transmit signal to improve the probability of detection. Okay, this is the first ingredient of sensing. Probably you say, okay, this is not, I mean, it's very simple. It's just transmit the signal and see if the signal has changed enough to consider that there is a target there in that environment. The second ingredient here is the localization. So this is more sensing. How can we define the localization? So the localization has 3 parameters. The distance. You can now imagine the classical radar image in which we have something turning around and detecting points, I don't know, submarines, airplanes, whatever you have in mind. We have to detect the distance. That means the time delay of the signal. I receive this signal, and I receive it after some nanoseconds, microseconds, so I can obtain the distance of the target. The other ingredient here is the Doppler frequency. So I can measure the Doppler shift and determine what is the velocity of the target. And third ingredient here is the angle of arrival and the angle of delivery. So the first measure in our mind here is the minimum square error. So for any of these parameters, I can calculate, I can obtain, or I can optimize, or I can minimize, the minimum square error. So this is again, remember that I am exclusively here in the fundamental limits of sensing. I'm not considering communications. I'm just reviewing what's happened for sensing. But instead of the minimum square error, typically we use the Cramer-Rao bound, which depends on the Fisher function. So basically, if we know the probability density function conditionated to the parameter that we want to estimate, we can obtain the Cramer-Rao bound here. And also, this Cramer-Rao bound in classical radar theory depends on the SNR and depends also on the amount of bandwidth and time of the transmitted signal. So here we have now many parameters in which we can play. Basically, the Cramer-Rao bound is the bound of how can I estimate something. Imagine that this parameter S is the distance, so S is the real value of the distance, and S hat is the error that I am the error that I am subject with this SNR and this value of bandwidth, time, and this W is the null beam. So this is classical radar theory. Then the last ingredient, remember that we have detection, location, and the third ingredient here is tracking. I detected something, I measure the distance, the velocity, and angle of arrival, and then I want to track that target, which makes sense. For instance, this is very useful for vehicular applications, for defense applications, for airplanes, if I want to detect, we have two options. Okay, we can be a radar to detect if somebody is driving with above the maximum velocity, but typically we want to track something. Here, basically, we employ the Bayes theorem to obtain the probability density function of the observation and the parameter that we want to estimate. And we apply basically the gradient and a Kalman filter. So this is a basic theory of tracking. This presentation is not focused on tracking, because if not, maybe it will be too long, and will be focused on detection and localization. And especially here, we will focus on how can we mix these two walls, because we have the Shannon capacity, and we have this detection and localization. I'm not going to discuss anything about tracking. It's okay. How can we mix sensing and communication? Because I have the feeling that everything here is not clear. I mean, we need to define a framework. So let's go to the beginning. Let's see what's happening in what the information theory can give us to provide a framework of this. So if we go if we design this problem as a Markov chain, basically we have a parameter to measure, to sense. We have a set of observations of the signal, and we have this estimation of the signal. So basically, we want to maximize the mutual information between our observations and the parameter that we want to measure. This is the same as for the capacity. I mean, this is the same game as for the communication or the capacity. If we go to the state of the art, there are some works that propose this very, very extremely simple framework in which the detection or the probability of failing the detection is inversely proportional to the SNR, and the communication follow the same equation as always, as the capacity. I mean, this is the state of the art. There are some people that propose this. But if obviously this is a very simple it's a simple approximation. Useful, because we can play with this. But let's see what happened. Probably you remember this from information theory, this kind of entropies and mutual information. So if you remember, this is the case of the capacity. We have the entropy of our source. This is the entropy of our output, our input, our output. This is the entropy of X given if we know Y, and this is the entropy of Y if we know X, and this is the mutual information. So we want to maximize the mutual information always. So how can we define the capacity? The capacity of communication. So the capacity obviously is given by the probability of detection. If it goes to the probability of failing the detection goes to infinity. That means that I am I am using all the resources for communications. And we have this. So basically, in this case, we have the mutual information of X given the X and Y, given assuming that I know perfectly the parameter that we want to estimate. This is the capacity of, if I know what we want to sense, what we want to measure, it's equal to the capacity. But we are including a third parameter here, a third guy. So if we use this scheme, we have our input, our output, and we want something to measure, to sense. So here, it's obvious that we have a mutual information for communication here, and a mutual information for sensing. It's obvious that we have a trade-off here. We can maximize the sensing and minimize the communication, and penalizing the communication. And if I don't want to send anything, I can maximize totally the communication. So it's obvious that there is a trade-off. We'll see later that it's a strange probability, a strange optimization problem, because it doesn't depend. It depends on the on the transmit power, on the power allocated for sensing and communication. But it's obvious that the solution to that optimization problem is transmit as much as you can. If you want to, I mean, transmitting more power here in this kind of problem doesn't solve the information theory part. So we'll see that we have we never have a maximization problem, because if we have a maximization problem of sensing and or sensing or communication, the solution is always the same. All the power to communications if you want to maximize communication, all the power to sensing if you want to optimize sensing. So we have to play with this optimization problem. Okay. Then for this byte, for this penalization, for this penalty of the mutual information that we use to capacity, we call it capacity distortion for ISAC. Basically, I mean, the idea is quite sensing, is quite simple, more or less simple, is that assuming a level of detection, we have this capacity. So we can fix a detection probability, and then we obtain the capacity for communications. And obviously, there is a penalization here. There is a trade-off between sensing and communication. So here, my point here is that I want to provide, again, a framework about what is sensing and communication. I mean, I don't know you at the beginning, when I started to study ISAC, I was a bit lost about what is, how can we do this? So we have sensing, that means detection, localization, and tracking. We have these three ingredients. Okay, but I don't know you, I don't feel comfortable with information theory. Sometimes it's tricky to me. I mean, I can understand it, but sometimes it's a bit difficult to play with it. So here, I will propose the metric of degrees of freedom. Probably everybody here is familiar with the communication degrees of freedom. Basically, a degree of freedom is the number of message symbols recovered by all communication receiver, which is also the multiplexing gain, or also the slope or the capacity or the rate. I mean, it's very simple. If I have two antennas and two users, I can send two data streams. That means that we are transmitting 2 degrees of freedom. If I have 3 antennas and 2 users, the degrees of freedom is still 2, because I cannot send 3 parallel data streams, knowing all the assumptions that we want to consider. If we add a third user and we have 3 transmit antennas and 3 users, then the degrees of freedom can be up to 3 if it's a broadcast channel, if the 3 antennas are collaborating between them. So the degrees of freedom, or the communication degrees of freedom, is given by the limit when the power goes to infinity of the capacity divided by the power. But again, I think that I never use this equation to obtain the degrees of freedom, just for checking sometimes. Is these three values. Obviously, using the degrees of freedom metric makes sense for medium-high SNR, or medium-high power. If we are working at very low SNR, the concept of degrees of freedom fails, because again we are talking about the slope of the rate. So well, Recently, we have defined, in the state of the art is defined the sensing degrees of freedom. That is basically based on the number of effective observation of the target, or how many times I can measure the channel. Remember that if I can measure the channel twice, I can improve my sensing capability. If I can sense in the channel 3 times, I can improve my sensing capability. So this Kramer-Rao bound is going to be lower as more sensing of the channel I have, because this measurement is also subject to noise. So basically, if we are talking about that we want, imagine a frequency division duplex system, and we want to obtain the channel matrix of 2 antennas and 1 user, it's obvious that we need 2 pilots, or we need 2 signals, one for one antenna, one for the other. Okay, so these signals, we assume that we have n different slots, and we can measure different orthogonal sensing signal. So basically, it's equal to sensing the channel. So now, I know that right now probably there are many questions about this. It's not clear, so I'm going to provide 2 examples of how can we obtain the degrees of freedom. So I think that will be more clear here. Let's assume this case in which we have KR communication users, and we have K sub T ISAC users. So basically here, in this case, we have the signal can be divided into communication part and sensing part. So that means that we are going to transmit information for communications and specific information for sensing. So let us assume this 3 users interference channel, in which we have the transmitter 1, transmitter 2, and transmitter 3. They transmit independently. It's not a broadcast channel. It's an interference channel again. And we have 3 users. These 3 users, this guy wants the message W1, this one the W2, and this the W3. So obviously, it's if we only use communications, the degrees of freedom is equal 1, because it's an interference channel. That means that in one time slot, I transmit to one user. In other time slot, I transmit to other user. In one time slot, I transmit to other user. And now we are adding a guy that wants to measure the channel of these three users. It's obvious that if I want to transmit an orthogonal symbol of the 3 transmitters, the sensing degrees of freedom is equal 1. So it's possible to demonstrate that the sensing degrees of freedom and communication degrees of freedom here it's equal to 2 divided by 3 for the sensing degrees of freedom and 1 for the communication degrees of freedom. And this is one of the open issues. I wrote down at least, because it's not demonstrated yet that this is the maximum. This is the outer bound. Probably it's the outer bound. It seems that it's the outer bound, but it's not demonstrated yet with information theory tools. Actually, this presentation, this value corresponds from a paper of 2025. It's not, at least as far as I know, it's not demonstrated yet. So let's use some assumptions that we can discuss later about these assumptions. The first one is that the communication channels varies in each time slot. So for communication, this guy, the channel changes in each time slot. In practice, we can use this we can assume this with this symbol extension. We can transmit, wait, a bit and wait until the users change it. But again, this is a bit tricky. Again, we assume, on the other hand, that the sensing channel remains constant because it's a sensor that is going to be fixed in some position, and we assume that is constant. However, note that these two conditions are difficult to satisfy, but again, this is a pure theoretical work. We assume that channel state information is known for the communication users. It's completely known. And also, we assume that the sensing signal is known by the communication receivers. That means that they can remove it. And we assume that we don't have channel state information for sensing because indeed it's what we want to obtain. So basically, this is the case in which we want to maximize the the communication degrees of freedom and the sensing degrees of freedom. Well, so if we focus on the communication degrees of freedom, basically means that each transmitter transmit a symbol to its users. That means that transmitter 1 transmit W to this user during the 3 time slots. This transmitter 2 transmit W2 to the receiver 2 during the 3 time slots. Transmitter 3 transmit W3 to the receiver 3 during the 3 time slots. So at the end, we have this channel matrix, and we have these 3 users. Why it's assumed that the channel changes in each time slot? Because if the channel doesn't change, this matrix will be a rank 1 matrix, and I couldn't solve this equation system. So I need these variants of these changes in the channel. Do you remember that at the beginning I said for communication we want a full rank matrix. We want a matrix with a rank as high as possible. Here, this is the problem. So we want to obtain this. If the channel will be the same, this equation system couldn't be solved. So that's why this assumption of changing the channel, it's assumed. And again, recall that during the 3 time slots, the users are transmitting the same. Again, we have 3 time slots, and this guy is transmitting W1 during the 3 time slots. This guy is transmitting W2 during the 3 time slots. Do you follow the idea? It's not, they are not using TDMA. They are not using time division multiple access. They are transmitting during the 3 time slots. They are transmitting the same signal. This is important because when we focus on the signal, that means that during the 3 time slots we can transmit 2 sensing vectors orthogonal between them, and this 4 is related with the sensing user. It's not a 4 time slot, this is 3 time slots, and we transmit this something with a similar structure to the blind interference alignment model here. So if we go to this, basically we are obtaining the channel times this is the signal received in the first time slot, and if we remove it with the 3rd and the 4th time slot, we can remove it. Actually, you can see that this is the signal, and we could remove this. Similarly, we could remove this signal. We could remove also this signal. So at the end, we can obtain our vector of sensing symbol for t equal 2. If we do it for t equal 3, that means the channel in the first slot minus the signal received in the third slot of the sensing signal, we could obtain the other value. So well, for this case, it's obvious that we can obtain 1 degree of freedom here for the part of communication. And if we go to the sensing, it's clear that we can detect or we can transmit 2 orthogonal vectors for estimating or measuring the channel. This is the case. The sensing degrees of freedom will be 2 vectors during 3 time slots, and we can transmit 3 messages, 3 data streams during 3 time slots. It's possible to demonstrate that for the k-user interference channel and only one sensor, this region is given by this equation. This can be demonstrated, but again, it's not demonstrated that is the optimum. That is the outer bound of this. If we compare these communication degrees of freedom and sensing degrees of freedom, we have a region in which this is the orthogonal, and this is the case that we have studied right now. Again, let us take into consideration that here we have a full channel state information varying the channel, which is not, I think that is not a realistic assumption. We'll discuss this. We will propose the use of reconfigurable antennas in which we can provide this. But again, moving to other example of sensing degrees of freedom and communication degrees of freedom, let's assume this broadcast channel with 3 antennas, 2 users, and 1 sensor. With 3 antennas and 2 users, it's clear that the communication degrees of freedom is equal to, I can send 2 parallel data streams. And only for sensing, we have 1 sensing degrees of freedom. So it's possible to demonstrate here that the region is given by a sensing degrees of freedom 1 divided by 2, and a communication degrees of freedom is 3 divided by 2. And here, if you want to obtain 2 degrees of freedom, 2 communication degrees of freedom, sorry, probably you say, okay, you have 3 antennas, 2 users. That means that during the first time slot, you can transmit to the 2 users simultaneously, and during the next one, you can transmit other 2 streams simultaneously. Remember that we want to maintain a constant transmit signal. I mean, this is tricky. I mean, the transmit signal is constant, but the channel is assumed that changes in every time slots. That's why I will propose the use of reconfigurable antennas, which is nowadays is an open issue. It's something that I am working already, so if somebody wants to work on it, I'm more than happy to collaborate. So we create this message W2 for user 1 and W1 for user 2, and we obtain the null vectors knowing the channel state information at the transmitter, as always. I mean, this is basic communication. Again, remember that we assume that the sensing signal is known by the communication receivers, so they remove that signal. And for sensing, I think that the solution is a bit simple, I would say. Basically, we transmit our communication signal plus the sensing vector, and in the other time slot, we transmit only the communication signal. That means that the sensor, the guy that wants to sense the channel, the sensing part here, can remove the communication signal, from the first time slot, just subtracting the signal received during the second time slot. Well, in this case, we need 2 degrees of freedom. Sorry, we need 2 time slots in which we can transmit 1 vector, 1 sensing vector. So that means that the sensing degrees of freedom is 1 divided by 2. And for communication degrees of freedom, we can transmit 3 degrees of freedom during 2 time slots. So again, we can, it's possible to demonstrate that it's not for the K user. There is a typo. There is a mistake here. It's not a typo. It's a mistake. It's for the broadcast channel, where M is the number of antennas and K is the number of users, assuming 1 user for sensing. This is the degrees of freedom area. That again, the theorem is that we can obtain this, but we don't know if this is the optimum, assuming that we know the channel state information. So we can think about if it's how can we demonstrate? I mean, even if we demonstrate that this is correct, perfect. I mean, it's a very good work. And as I commented before, I am already working on the use of reconfigurable antennas. And I can demonstrate that this is also a typo here. This is the communication degrees of freedom is mk divided by m plus k minus 1. And the sensing degrees of freedom is 1 divided by m plus k minus 1. That means that assuming that we don't know anything, we are totally blind, we don't know the channel state information of any user, this is our region. So using channel state information of the transmitter, which means that we are wasting network resources for measuring the channel of the users, we only obtain this gain. So we can discuss, I mean, again, this is something in which I am working already. And the idea is to use reconfigurable antennas. Actually, this use of reconfigurable antennas can go beyond the analysis of the degrees of freedom. And probably you think that this degrees of freedom is again too theoretical, which is true. I mean, it's true that this is very, very theoretical. And so in the next part of the presentation, we will discuss about how can we simulate this and how can we optimize the network resources, mainly the power. But again, keep this in mind when we are using, when we want to employ ISAC, we are always thinking about this structure. So we have random bits for communications, and we have sensing symbols that are known, are deterministic for everybody in the system. We apply some precoding, and we have the wireless channel for communications, and we have the sensing channel. Some results about this paper, I will include the reference at the end of the presentation. The channel estimation, this red line is assuming that we estimate the channel without managing the interference. Obviously, we are limited by interference. And here means that the channel estimation error is lower as the SNR increases, which makes sense with the Kramer-Rao bounds that we discussed at the beginning of the presentation. As the SNR increases, our estimation becomes better, which makes sense. But also becomes better if we use more bandwidth or we are playing with the time of transmission. So again, okay. Probably you are thinking, okay, this is information theory, degrees of freedom, this is too tricky. I don't like information theory. I mean, it's normal. I heard sometimes that information theory is like poetry, and nobody likes poetry. So how can we simulate this, or how can we optimize this from a communication point of view? So let's assume that we have, I know the notation, I'm changing a bit the notation to follow my notes. Let's assume that we have K communication user, Q sensing targets, and L ISAC users. So we have people that only want communication, people that only want target, only want to measure the channel, and people that want everything. So the transmit signal is a vector given by all these guys, the K, Q, and L users. And we can apply a precoding as usual. I mean, this equation, we have been using this equation, I don't know, 20 years. We can precode the signal. And for ISAC, something that, I don't know, I didn't use it before. We have the concept of epoch. That means, do you remember, bear in mind the concept of this radar. Okay, yes, give me a second. The concept of this radar. An epoch is basically each time that I am turning around my radar. This is what we call it, epoch. In each epoch, I can use the information that I obtained in the previous epoch. So that means that if I have something that if I could measure interference in the previous epoch, I can assume a sensing, I will call it a sensing coherence time, in which I can, okay, this doesn't change, I can remove this interference. So I know that this doesn't move. So for the receive baseband signal, you have this equation. I included all the parameters that I think that we can use. This is the beamforming at the receiver, assuming that we have more antennas. This value kappa is the array gain. It's proportional to the number of antennas at the transmitter and the receiver. This is the power allocated to the target Q. Remember that I am thinking this is the signal received by the target. This value alpha is the reflection gain. Is I don't know, the reflection of an airplane is not equal to the reflection of a human body, or we need to consider this radar cross section. This is given by the Doppler. This is the beamforming equations, assuming here I assume a uniform linear array for the transmitted signal and for the received signal. This is the symbol or the signal that I transmit. This is the delay of the transmit signal. Remember that I need this delay for measuring the distance. This Doppler for measuring the velocity. And this amount of power for measuring to detect, not for measuring, to detect if there is a target or not. So here we have these three ingredients of ISAC. The signal detection, that means the amount of power in some specific direction, the velocity, and the distance is here. So we have to play with this. And obviously we can point some beam in a specific direction or in other direction. So it's obvious that if I am pointing to some direction that I don't want I know that there's nothing there, I am going to measure always noise. So we want to point where we want to transmit. That's why the image that we have of radar here is turning around, because it's basically a very narrow beam that is turning to measure all in every direction. So this is for radar. For communication, we obtain something similar. This value kappa is the array gain. This is the power that we allocate to our user. This alpha is the channel gain of our system. This is the Doppler. This is the precoding, the beamforming at the user. Sorry, the receiving beamforming. This is the precoding of the signal, if I remember correctly. This is the signal that we want to transmit, and this is obviously the noise. In the best case, we can align the beamformers. That means that the beamforming at some transmitter is aligned with the beamforming at the receiver, so we can simplify also these equations. If we assume this simplification of the signal, we can obtain the SNR of the capacity, where again this is the power to the user, this is kappa, which is the channel, the array gain, alpha, that is the channel gain, this is the post coding at the user, this is the precoding, sorry, and this is the alignment between the beams. And here we have the bandwidth that we allocated to that user. For instance, if we play with the bandwidth, and this is the level of noise, the spectral density of the noise. So, well, I mean, this is we have many parameters, but it's the problem. It's a usual problem for us. I mean, it's something that we want to obtain. So, how can we move to optimize this SNR? If you remember, at the beginning I said, okay, this optimization problem is tricky, because if I want to optimize to maximize the probability of detection, allocate as much power as possible. And if I want to maximize the capacity, allocate as much power as possible. So usually, or the easiest way to manage this optimization problem is assume the capacity, some capacity or some rate of the communication users. So these communication users goes to the constraints, to the constraints of our optimization problem. Okay, I want this user to obtain this amount of power. I don't know. This amount of rate, I don't know, 1 bit per second per hertz. Okay, if we have here the bandwidth, I don't want that every user obtain at least 10 kilobits per second. Here the classical constraint that we don't transmit above the total power, and we are subject to the bandwidth that is allocated to this system. And then I want to maximize the sensing quality of service, detection, localization, or tracking. Well, let's try to simplify this because we have many parameters. For target detection, we assume, again, one specific direction, this theta sub q. We know that the information from the previous epoch. We know if somebody was there or not. We know the reflection coefficient that is related with the radar cross-section, how many energy is reflected from the receiver, and we assume this epsilon q that is the alignment of the beamforming at the transmitters, and this epsilon tilde that is the alignment at the receiver beam, because of the receiver of the beamforming. And also we assume a spatial temporal match filter. That means that we can remove the Doppler. So again, this is for detection. We remove this Doppler, and we have this hypothesis test. This is our signal, and if nobody was there, we receive only noise. If we detect something, we receive this amount of signal. We can define a threshold for the false alarm, and we can apply this Neyman-Pearson theorem. If we want to check this with the probability density function, we have the sum of two square Gaussian variables. That means a chi-square distribution with 2 degrees of freedom. If we have 3 variables, it will be 3 degrees of freedom. I mean, this degrees of freedom is related with the chi-square probability density function with the chi-square variable. So if we want to use, if you remember, when we use this in when we were studying the degree, we use these Gaussian variables, and we define the threshold, and we play with the Niemann Pearson detection. So here we do the same, but we are more sophisticated here. But basically, we define there's a typo there. We define the false alarm, and we optimize the detection probability. So basically, here we have two optimization problems, where, again, look at the constraints are always the same. We assume that this is the power constraints and bandwidth constraints, maybe, and we have some minimum rate for each user. And the problem just want to maximize the amount of power that we are transmitting in the direction of that we want to detect if there is a target or not. I mean, it seems more complicated as we believe. I mean, it's just I want to allocate the users to manage the power so that they satisfy some constraint. We need to check if the problem is feasible, obviously, because if this condition is too high, it's not going to be feasible. And we want to optimize once we have satisfied this, the remaining power, we want to use it for detection. That means, okay, other beam here, other beam here. This is I simplify this optimization problem. Here we can play with the beamformers, with the precoders, with the postcoders, there are many degrees of the design that we can play here. And we call it these fairness optimization problems, and if we want to, because we analyze each user target by target, and here this is the comprehensiveness optimization problem that it maximizes the sum of the detection. This problem is not the same because of the presence of ISAC users, because ISAC users also want data rate. Be careful here. Here in this communication rate, we have communication users that are here and here. We have ISAC users that are also here. And we have ISAC users that are not here, that are also here, sorry, and are also here. So basically, ISAC users want everything. We have communication users that are only in the constraints, detection users that are, or detection directions or detection targets that are only in the objective function, and ISAC users that are in both, in the communication and sensing users. And if we go to some results, remember that we define the probability of false alarm. This is probability of 0.01, and this is the probability of detection. If we add a greater threshold for a greater sum rate for the users, this is the rate of the users, we are allocating less power for detection. That means that, okay, this is probably here the problem becomes unfeasible because we are allocating all the power to communication rate. So we have to find a trade-off between probability of detection, probability of false alarm, and amount of communication. So probably the optimum or the Pareto optimum will be something like here. We are not losing too much the probability of detection, and we are still maximizing a bit the communication rate. Here, the same. You can see that the results are quite similar. The behavior of the plots are very similar. and the rates are similar using the comprehensive results. And okay, that was for detection. If we move to localization, we have this problem that we want to maximize the we want to measure, the time delay, the Doppler, and the angle of arrival and angle of delivery. So we have these Kramer-Rao bounds that now we know that the SNR, we know the SNR of our system, and we know the bandwidth and the time of each signal. And here is, if you remember, I said that we can play with the beamforming. This optimization problem was more illustrative than a design problem. So we have to play with the number of antennas and the beamforming that we are developing. So if we have a simple beam, 1, 2 antennas, we have everything here. If we have a small-scale MIMO, maybe you have more users, or we have to play with the interbeam interference. If we have a very massive system, we can create very narrow beams. So, I mean, this is not clear. I mean, this presentation is just to provide tools and open problems. I'm not going to solve this. But the good point is that if you don't want to play with the Fisher function, we can approximate the Kramer-Rao bound. We don't need it's not necessary to play with or start playing with all this Fisher function, which is not friendly. I mean, it's not friendly as this one. This is very friendly. So basically here we have our SNR depending on the bandwidth, and we can also minimize the Kramer-Rao bound, maximizing this value where the Kramer-Rao bound goes to the denominator. So this is this omega normalization problem. So I mean, we can apply the same optimization problem that we saw before, this comprehensive optimization problem. We can apply it to this problem, and imagine that we have these results where we have the base station. Here we have one user, other user, one target, and we have an ISAC user. So it's obvious that if we increase the data rate, we are increasing the Kramer-Rao bound. That means that we are increasing the error in the measurement of our parameters. I mean, what I want to show here is that even with this problem, this optimization problem, we can see that there is a trade-off between communication and sensing. And well, it's more than 1 hour about what is the future research lines, which are the issues in which I am working right now. The first one is waveform and beamforming the design. So there are still things to analyze here. We have the different beamformers or precoders, play with the number of antennas. We have many things to analyze, and we can optimize the communications under radar constraints, optimize radar under communication performance constraints, or find something some Pareto optimum point in which want to optimize radar and communications simultaneously. Other research line is the fundamental limits and the use of reconfigurable antennas. Probably if you know my works, I used to use these reconfigurable antennas or reconfigurable receivers. So here we have many scenarios to analyze: monostatic, bistatic, assuming channel state information, partial channel state information, no channel state information, how narrow are the beams. We can assume that we can allocate one beam per each user subject to some discrimination level without avoiding the interference between beamformers. So there are many scenarios here to be analyzed. And again, there are not many information theory works about ISAC. I mean, although there are many works analyzing again the optimization problems, analyzing the fundamental limits of ISAC. I think that is something that is still unknown, that we can take water from that well. And I mean, I usually start with the Fano inequality here, and this is the usual methodology to obtain the degrees of freedom. And finally, other thing that we are working with Borja and Alejandro here is optical ISAC. So it's obvious that radar becomes LIDAR, but the idea we use, I mean, the optical signal, especially the non-coherence optical signal, has a bad propagation. I mean, the propagation is not very good. We have few meters for channel propagation, so we dope the reflection using retroreflective corner cubes or sun reflectors in general. So we want to reflect the signal. Imagine that we have something, a car done with plastic is not reflecting too much electromagnetic signal. So we are covering our target with metal, which in this case is a retroreflective corner cube. That is something that reflects a large percentage of signal. And this is one of the preliminary results that Alejandro obtained recently. That is assuming a single LED equipped with 5 or 4 photodiodes. I don't remember. I think that 5. We can obtain a very, very accurate positioning here. And how can we measure this positioning? Maybe will be used for knowing where the target is, or for applying some precoding based on the position of the users. And I think that that's all. I have these three open issues in which I'm working already. Probably there are many more than this one, but I will be happy to discuss these 3 or others. I will be more than happy to discuss any issue related with ISAC. So thank you very much for presenting. If you have any question, okay. I'm going to repeat the question for the audience in. Okay.
I think they are pretty basic. Well, first of all, thank you very much for the presentation. At the very beginning, you described the sensing channel. So how different is the sensing channel from the communication channel, and how you model the sensing channel?
It's the same. It's the same. It's the same channel. The problem here is that we used to consider the Doppler, and I will go here. Okay. The channel is basically the same. Is the communication signal is subject to the same effects. It's subject to Doppler, it's subject to delay of the signal, and it's subject to some SNR. But typically, we try to eliminate, to cancel all that effects. We want to cancel the delay, and we want to cancel the Doppler, because it's something that is hampering, that is not good for detecting the communications. On the other hand, when we go to ISAC, we are also subject to Doppler, we are also subject to the delay, and we are also subject to some SNR. But the difference is that we want now to estimate that. I mean, the channel is the same. The physical channel doesn't change. The only thing is that one channel, for communication, we try to cancel all these effects. And for ISAC, we want to measure them.
So, and you have modeled this problem as like a power allocation problem where you have some power allocated to sensing and some power allocated to communication. How far we can, is it possible also to reuse the communication signal, or how far we can go in sensing by reducing the communication signal? I mean, do not allocate a specific power to sensing, but reducing the communication signal for doing some sensing tasks.
Yes. So if I understood correctly, the idea is, okay, we have only communication signals, and we want to reuse that communication signal for sensing. Yes, we can do it. We can assume that we don't have any target. We don't. Okay, we have that target, but for the precoders, we are only considering the precoding for communications, and we assume that only only information is transmitted for communications. And if we are lucky, in that direction, we will receive some signal at our target. But again, this depends on the beamformers. If we have a very narrow beam, the probability of that occur is low. That's why I said at the signal model case, this one, that will be this case. Can we reuse the signal? I don't know. I mean, I haven't analyzed it, but we can do it.
Thank you very much for the presentation, Maximo. I think it was very, very clear and very useful, and I think the topic is very timely, of course. I have just some minor questions related, first of all, to slide number 10. If you can go back. Okay, here you were just talking about the difference between detection and communication. And in the detection, you say, I guess this parameter D represents the probability of detection or something like that, right? And I wonder why it is an inverse with the SNR. Of error. I thought it was of success of detection. So I thought the better SNR you have, the better detection you will have. Okay, it is the error. Okay. And then if you go to slide 28. Yeah. Well, I mean, this question is related a little bit with the question Borja asked before. Here, it seems that you have, on one hand, receivers for the communications, the communication part, and sensors for the sensing part. At the end, what you need for the sensing part is the knowledge of the channel, right? So, but for the communications, you also need the channel if you are doing coherent communications, because I assume you are doing coherent communications, right? So, I think that maybe these two receivers could be joined in some way, because at the end, what you need for communication, because for communication you need knowledge of channel estimation, and maybe they could be mixed, because now you are for the to create the communications and sensing part, you are splitting in power or in your resources are split, right? You do the communications part, and maybe you reserve some resources for the sensing. But you split in something or in time? You put pilot spatially. You do this spatially.
Right now, I assume that the channel is known.
Okay.
I'm not assuming the system of transmitting. I'm assuming that the channel is known, and during the transmission of
Okay.
data, I receive the sensing. The question is okay. Sorry. So I was commenting that I assume that this sensing part is given by, corresponds also, occurs simultaneously to the transmission of data. If we go to the sensing part, if you remember from here, from this area corresponds to the area in which I'm transmitting data, and simultaneously I'm transmitting that sensing signal, which we can call it pilot. I mean, this is not new. I mean, we can call it, I will remember the name, this idea of transmitting pilots and data simultaneously. So, do you remember the name? Sorry. Superimpose. It's a kind of this is a kind of superimposed signal. So the idea is that we are, instead, I'm not an expert in superimpose. Maybe I'm failing here, but the idea is that instead of managing the interference because of superimposing pilots and data, here we are canceling both. So here in this case, this degrees of freedom means that I am canceling the signal for data and the signal for sensing. Here with the transmission structure, here in this example, and which is a beamforming at the end. Yes, this is a very simple beamforming. Yes, it's a precoding. It's not a beamforming. Yes. Yes, because sometimes this works. Be careful here, because they work about the beamforming, about the pointing to somewhere, and I mean they assume a kind of hybrid precoding in which we are pointing to some direction. We have the digital precoding. Thank you. More questions?
Thanks a lot, because having all this information all together is extremely useful, and I think we all learned a lot. And of course, there are a lot of questions because you talked about so many things. Actually, I have the same question, or very related, because this work always assumes the sensing receiver and the communications receiver are in the different positions. But why? Because I think if they are together, this is what ISAC means. I mean, ISAC means minimizing as much as possible the resources, right? So if you really use the same receiver as well as the same transmitter, if it is possible, it depends on the application. And in this case, I think, well, everything is going to change because now the channel is not different. So you need to find other ways. But also, all this work is completely neglecting the fact that you need to estimate the channel for the communications. So if you consider that you need to estimate the channel for the communications, then you gain by having the receiver of communications and sensing on the same place. Of course, I mean, you need to start from somewhere, and maybe it is difficult. But I think someone should take into account that the channel is not known at the receiver. And then the same problem is being solved by both. And there is this, I mean, someone has to take care of this, because otherwise it's always useful. It's always useful to have bounds and to know, but I think this is too much idealistic, as usually happens with information theory. But information theory can also take care of the channel knowledge, right? And if you can have a look at this, because I think we are clearly missing here an important point. If you want to, I have more questions.
Yes, here, maybe I'm wrong here. I'm starting to read this, about this. I have here, there are some assumptions that I heard. I don't know if they are true or not. First one, current systems are using TDD. So that means that they don't need, they don't transmit pilots from the base station. But as you said, we are missing the coherence detection pilots that are transmitted in some. But I heard this. I mean, this is one assumption that I've seen, that these systems are TDD. That means that the pilots are mainly transmitted from the users to the base station. So we have to add this sensing. Another one is what we call it this coherence times of the sensing. We are assuming that the sensing varies faster than the transmission of pilots, which again is very idealistic. I mean, it's an assumption, because in this assumption we assume that the sensor, the channel of the sensor remains constant, because we say, okay, it's a sensor. I mean, so it's tricky. So I agree completely here. If the usual transmission, if the closed loop transmission that we have seen, okay, we can discuss about how often, how we need to refresh the pilot transmission. We can discuss about it. But again, if that transmission of pilots, which is what we are doing here, this degrees of freedom is sensing degrees of freedom is. The problem is that I am assuming that we are assuming something orthogonal. We are assuming some time for pilot transmission, and after that we transmit data. It is the case that we have considered here. In this case, we are assuming that data is transmitted simultaneously with the channel. I don't know, to be honest. I mean, I need to I mean, it's necessary to justify and say, okay, for very low latency, this could be useful, maybe. If latency is not a big issue here, or the coherence time is not a big issue, maybe you can assume, as always. Or where is the threshold in which this is useful, or we can split. I mean, we have been 60, 80 years. Sorry. We have been 60, 80 years using radar and communication independently, so we should justify this.
This consideration about the different coherence time and the TDD makes sense. There is a lot of FDD spectrum, but okay. Another question is about the degrees of freedom. In the degrees of freedom in communication, it is extremely clear what they mean and how they are related to the objective of the communication, that is transmit information the fastest you can. So if you transmit if you can multiplex, it is clear what you achieve. But I don't see this relation in the case of the sensing, because I want to detect something. What is the relation of how many times I can transmit towards the target and the probability of detection or some other parameter? I don't see that clear.
It assumes that if we increase that degree, the sensing degrees of freedom, we can measure the parameter more accurate. We are subject to some error. If we do it again, we are reducing the Kramer raw bound. So if I know if I'm measuring the distance, I can be more accurate measuring the distance if I have two measurements of this. I take the average of them, for instance, and I will be more accurate than only one. I don't know. I don't know. No. The audience is asking what is the relation if I have 1, 2, 3, or 1,000 measurement of the channel related with the Kramer raw bound, if it's linear, logarithmic, or so. As far as I know, I don't know. I mean, it's I need to check it.
Last question, I think. In the slide 44, Don't go for it. It is just you show some approximations of the Kramer-Rao bound, and my question is, when can you use these approximations? They may work in some particular conditions, or because it's very useful to just use this instead of doing all the work.
Yes, Gaussian parameters, estimation if Gaussian, we can use this equation. They are also subject to some, I didn't write it, they are also subject to some variance error because of using this approximation. The parameter, the estimation of the parameter is, yes, yeah, exactly. Yes. No, I don't know. I mean, this is the measurement. I don't know if yes. If we want to analyze this, we should go to a radar, a pure radar book or work, because probably I found that many things that are related with ISAC corresponds to radar, and radio determination is not even a subject nowadays. So we need to visit again that works. Okay, more questions? Okay.
Hi, Maximo. Thanks for the talk. Just a quick question. How important is the angle of arrival or the angle of determination? Because we need to know the velocity and the delay, and the angle, is that important, or it depends?
So basically it depends on how narrow is the beam. If we have a very narrow beam, we want to know the angle of arrival and angle of delivery for pointing to that direction. So it depends a lot on how narrow are the beams. Which depends on the number of antennas, of course. More questions? That's good. I mean,
So thank you for the talk. It's very interesting, and it's all the information theory is very difficult, but it is very good to have these fundamentals, right? So thank you. I really liked it. Sorry if you already answered this question, because maybe it was difficult for me to follow. But you said that the degrees of freedom or the Kramer bounds define the sensing in terms of how well we estimate, in terms of how many times we do it, and taking the average or something like this. But and you also talked about we do it better if we have a narrow beam in terms for the angle, no, for the angle and everything. But are we considering here also that we need the sensing signal to have as much bandwidth and also time occupation as possible to have the good resolution? Is this embedded here?
no, here basically we are discussing about how many times I mean, the degrees of freedom actually is not related with the powering for communications. It's related about how many data streams I can transmit simultaneously. So the idea is to have a very fundamental metric about how many times I can sense the channel. And here, we are not considering power, angle of arrival, distance. We are simplifying the transmit signal as much as possible to obtain this. So the answer is that we are not considering that in this metric, in the degrees of freedom metric, which is again something related with the fundamental limits of simultaneous data and sensing. Yes.
The question comes from Nishi. Do you believe that it's feasible to have the technology for supporting this technique? What frequency bands are we talking about?
About the technology, my answer is why not? Why not? I mean, we have done radar and we have done communications with all of this. Why not? I mean, probably we cannot do it efficiently at the first time, but we are subject to some duplicity of radar. I mean, if I imagine that I want to implement this next week here in the lab, I will buy a radar system or a LiDAR system that will be cheaper, and a communication data. We can see if this is feasible in optics with a low budget. So I think that it's feasible. About the frequency bands, honestly, I don't know. I don't know if probably occurs the same as in communication, but this is only my humble opinion. Obviously, we can use more antennas at a higher frequency, at millimeter waves, so we can assume more narrow beams, and we can play with these beams. If we have at lower frequencies, if we are, I don't know, in 800 megahertz, we have a wide beam, and then we have to apply other kind of ISAC. So I think that it depends on the frequency bands that are available for doing this. Okay, so I think that's all for today. Thank you so much for attending, and I close here.